Okay, so let us talk about the test. It does open up today, but you don't have to take it until Friday if you absolutely don't want to. As a reminder, there is no lab this week, so do please spend the time studying, resting, honors daying. That's totally a verb now. In lecture this week, we'll be focused first and foremost on talking about any test-related topics and questions that you have. If you attend lecture and no one has any questions, if there's no more material for this specific test to go over, then I'll begin talking about light and sound, because that at the very least is what we're going to be lecturing about next calendar week. So I'd like to go ahead and be discussing either that or probably the exam. As a reminder, let's see. This is currently test week. It'll open up at 1:30 today, and you can take it at any point before midnight on Friday. I recommend you take it when I'm likely to be awake so that I can give you answers over email, to questions over email. But otherwise, when you take it, it's up to you. Once you open it, the 5-hour timer will start. It's designed to take you 1 hour, but fine. It's just to account for the fact it takes longer for me to get back to you, and you'll be interrupted by X number of possible things. Next calendar week, we will have a normal lab where we're finally going to build those electric motors. And we'll be talking about all the basics of light and waves and sound that you would need to know to exist as a human on planet Earth. And then the week after that, we will close everything out and make sure we're ready for the exam. So, as for today, and I have some specific things that we can look at, but to start with, you've already been asking some good questions. Is there anything else specific you guys have on your minds about this test today, or this test this week?
I know you had said last class about the charge and the mass of the electron. I just didn't see if you did put that. Did you put it on there, or do I need to
No, okay.
memorize?
You do not need to memorize them. I only remember them because I've been using them so much recently. If you ask me in the middle of summer or next semester when I'm not teaching it, it will have exited my brain. Please keep heckling me about this, because it's not that I am planning and will upload a table of constants and such. Things just slip my brain if I'm not actively thinking about them, which is entirely a me problem that I need to work on. It's not your responsibility, but that is something I am going to do, at least for right now. I think that allows you to look at the notes on assignments in the past. At least for right now, I do already have started the electricity notes. Now, within your chapter 15 notes, there is a table with the relative mass and charge of each particle on it. And this is information that, again, these are known constants. So this information is at your disposal. It's fine if for some reason the document I'm going to upload isn't there in time, then this is free to look up information. A constant is always constants, things that universal fundamental parts about specific materials or particles that are known things are considered at your fingertips at any given moment. You can look them up if, heaven forbid, I don't upload something fast enough. I know on the particular test there is one specific thing that you will need that I'm going to go ahead and look up in a second. Right now we have on screen, which will be available to you on the constants document soon, charge and mass of each of the 3 subatomic particles. And there is a unit of measure that is going to appear on the test because it's baked into a lot of other science questions, and I can't really code it back out. So there's a unit that will appear that I haven't talked about recently because I don't much like it, but the unit is units of electron volts. And it is rather confusingly a unit of energy. I suppose you could say it's the energy that one electron has while exposed to 1 volt of potential. And since it's a unit of energy, we can't convert it to joules.
When exposed to 1 volt?
Correct. This unit was invented because even though subatomic particles move very fast, they have a very small mass, so no one particle has a whole lot of energy within it by itself. And so this unit was invented so that we could talk about the energy of particles in whole numbers of electron volts instead of in weird numbers of times 10 to the negative 19th scale. I'm not a huge fan because we use joules for everything. Might as well just keep it that way. But at least for the sake of this particular test, there will be energies listed in electron volts, and this is how you convert it to joules to be able to do the rest of your math. This will also be available on the constant document that I upload. Speaking of, I guess, information that you will probably need, I've realized something. After forgetting my own formulas 8 million times. Remember on the last homework where we would use this formula for the orbital radius of a charged particle that is now spinning in a circle because of the force of magnetic field constantly changing directions, combination of magnetic force and centripetal force. Phys1510 was using this formula for all of its answers because it turns out this is the correct formula. All of my notes have the squared in it, but when you actually combine the 2 formulas together, the squared from centripetal force gets canceled out by the velocity inherent in the other formula, and it just results in there only being 1 V here. On the online study sheet, I have rectified the formula, but if anywhere in your notes it still says V squared, that squared technically needs to be. And I apologize because that's the formula I've been showing you for weeks, and it slipped through my fingers, and I'm sorry. I also made a different mistake. Phys1510 wasn't wrong about where the z-axis is. I was just holding my hand wrong. Or rather, misreading the question. a lot of the problems with last week's homework were actually problems with me. So that was an interesting exercise in introspection.
Wait, so the positive Z is out of the board?
Yes. If positive X is this way and positive Y is this way, positive Z is out of the board.
Can you like, show us like the point, like the dot versus the X on a magnetic field to know like which one's in, which one's out?
Yes. A dot, sometimes a dot within a circle is meant to mean outwards. It's like the tip of an arrow firing towards you. Occasionally it will be represented by a series of dots or a series of circles showing multiple lines pointing out towards you. Meanwhile, a series of X's represents inwards. That's meant to look like maybe the tail feathers of an arrow firing away from you, or possibly the hole in the paper after you fired an arrow through it away from yourself.
We skipped 18.
Oh, yes, in chapter number, I combined 17 and 18 together. I took the pieces of 18 we needed and taught them in 17. And then 19 started back.
Can I ask you something about 17?
Yes.
Okay, so, I understand the formula for resistors, for total resistance for series and parallel.
Okay.
But like, can you explain again the trend with current and velocity, or voltage, and like how it changes once you go through it versus like right before?
So voltage and velocity, voltage and current in different circuit shapes?
Yes.
Okay, yes. So you've got series, you've got parallel. And the rules for each, which I'll try to put in bold, in visible colors. In parallel, every resistor will get the same voltage drop, but a different piece of the current. In series, everything gets the same current and a different piece of the total voltage. What's wrong with my spelling today? Different piece of total voltage. The reason for this, within series, if, say, for example, 10 amps of current exits the battery. All three of these resistors are going to get 10 amps of current through them because that current has to go through each one sequentially. So the flow is not diverted, it's not lessened, it has to go through all of them. Like a big raging river that has to go through every lock and every water wheel down the length of the river. Doesn't have any other choice. Yes?
Wait, I think what I get confused is, so you can have like the same current, but you, like, okay, like potential, like voltage, right? So you have to have a voltage difference for it to go around, right? So like the current, the total current remains the same, but you do need your voltage to go to zero, right?
Yes. In series, that voltage will decrease one piece at a time. So let's say, let's make life a little bit easier on ourselves right now. Let's say this is a 9-volt battery, and all of these resistors are the same. They are all the same type of resistor, like R equals 100 ohms or something, just wired in series, just for simplicity's sake. And let's say, okay, let's say these are all 1 ohm. So their total resistance would be 3 ohms, which means the total circuit current would be 3 amps. Sorry to change the numbers. I think this is just a little, makes the numbers a little simpler. So the total circuit resistance, in series, they're all going to, these three are going to add up to one single resistance, and they're just going to add up linearly in series. So a total resistance of 3. Voltage equals current times total resistance, so that means the total current should be 3 amps. And because they're in series, every single resistor is going to get 3 full amps. The amps have to go through all of them. When looking at circuits, we have the one formula, V equals IR for Ohm's law, but typically you're going to need to use it in 2 different contexts. You want to look at, one of those contexts is the whole circuit. So V total equals current total times resistance total for the whole circuit as one lump sum. But then a separate context is using it to look at what happens for a single resistor at a time. And for single resistors, you care about its specific voltage, its specific current, and its specific resistance. Now, based on what type of circuit you're looking at, some of these numbers will be the same as these numbers. In a series circuit, the total current is the individual current, whereas everything will have a different resistance and a different voltage drop. In this particular circuit here, since we know that the total current remains the same, every resistor here is going to get 3 amps running through it. If we were to plug in that known 3 amps and each known resistance of 1, each resistor would have a voltage drop of 3. So every single time the current goes through a resistor, the voltage will drop by 3. Which gives us a total drop across the whole circuit of 9. So across the whole circuit, we go from 9 volts on one side of the battery to 0 volts on the other side of the battery.
But your current is still 3.
Yes, the current will remain unchanged because it's a series circuit.
Okay, so for like the parallel, I get that your voltage has to be 0 at the end, but is there the same current before going through the resistors and after you went through all the resistors?
Yes. So for this circuit, let's keep the same numbers just to show the differences. You have a 9-volt battery, 1 ohm resistors, although that's going to make our resistance super tiny. Yeah, our total resistance here, doing that math quickly, is going to be 1/3 of an ohm. Yeah, very small. If we do V equals IR for the whole circuit, then the total circuit current is going to be 27 amps. Am I doing that right? 3 times 9, 27.
Did not.
total circuit, just to find that total current. Multiply both sides by 3, current equals 27 amps. So total current is 27 amps.
I guess I just don't get how you can go in with 9 volts into each separate like parallel branch, right? And then come out with 0. Like, how did 9 volts go through each one?
I'm trying to think of an analogy I haven't used yet. Okay. This is going to be a kind of a wonky attempt at drawing a three-dimensional picture. I apologize for my art skills. I'm going to compare each of the circuit types to different waterfall configurations. So, let's say in series, we have 3 different pools, each of them one after the other. Every single time the water jumps down a pool, some of its potential gets used up. It has less potential down here than it had up here. But each individual time, it only dropped a piece of the total. In parallel, that would be more like if instead of having like